Okay guys, today we're doing 4.12, Intermediate Value Theorem, which we can just call IVT. Now I consider this to be a pretty simple theorem, so I'm also going to throw some MVT in there as well, so you can see the two theorems that they most test on the exam together, which is IVT and MVT. MVT being what we learned yesterday, or the day before, I can't remember, but MVT. Okay, here, let's go forward. Okay, first off, let's remind ourselves of MVT, what it says. So if a function is continuous, meaning we can draw it without taking our pencil off the paper, right? And differentiable, meaning it's smooth everywhere, there's no sharp turns. There is some number c in between a and b, such that, let's just remind ourselves here, that is, that the instantaneous rate of change is equal to the average rate of change, right? And what does that mean? Algebraically, that means that the instantaneous rate of change, which means derivative, right? That's the definition of instantaneous rate of change, is equal to the average rate of change, which is f of b minus f of a all over b minus a, which is also the definition of an average rate of change, right? Now, graphically, we spoke about what that means yesterday. That means that the instantaneous rate of change, so that means that the slope of the tangent line will be parallel to some average rate of change or some secant line, right? And that is what that means. The instantaneous rate of change is equal to the average rate of change. Okay, so let's go on and talk about what IVT is. Now, first here I have the book way of saying it. I'm going to first explain it with my own definition here, and then I can try to explain it with what they're saying. Now let's say I got this graph right here, and let's say I'm going from here, I'm trying to go from that point to, let's say, this point. Okay, so I'm going from the x values 0 to 3. Yeah, and that would include the y values of in between there, right? Now, if a function is continuous, meaning you have to draw it without taking your pencil off the paper, yeah, you have to go through the other values in order to draw the next value. If a function is continuous, what this means is that in order for me to go from this point to this point, I have to cross through all the x values in between those 2 points. That would be way over there. So I have to cross through every x value between 0 and 3. Yeah? That also means I have to cross through every y value between those 2 points. Yeah? So every y value from, it looks like about negative 1.5, all the way up to 3. Now that's what, if it's continuous, you have to cross through everything. And that comes to terms with, I kind of switched the name of this. Instead of intermediate value theorem, I kind of think about it as in-between value theorem, because it means that we have to cross through everything in between our points in order to have a continuous function. Now let me explain how the book does. It says if there is an n value, okay, they're talking about the y value, so just grab a y value in between here. We'll call this the n value, okay? If there is an n value between f of a and f of b, now that would be my y values, f of a, and then this one would be f of b. Okay, so we're saying that n is between f of a and f of b. Then there is some c value between a and b. So a is my x value for that same y value, and b is the y value for that. It's saying that there's some x value, which we were saying this is going to be our n, so our x value would be right around there. That's where our x value would be. This would be, or we're calling it the c value. C value, where f of c is equal to n. So it's just saying that you have to have any x value in between here has to be crossed through, and you have to have any y value through there has to be crossed through. So really the way to think about this is you have to cross through all x and y values between the points in order to have a continuous function. So here's another way of saying it. If your function has a point 0, 0, that's 0, 0, and a 0.11. And you have to go through all the points in between to get to the other point. So I have to go through everything between 0 and 1 on the y values and everything between 0 and 1 on the x values in order to get to this other point. There's no way of doing it, and no other way of doing it. I mean, I can make it go down, I can go through other x and y values, but I have to go through the 0 to 1 x's and the 0 to 1 y's in order to get to this point. Let's see how they might test it, okay? So if f of x is differentiable on the function f of 2 equals -4 and f of 3 equals 5, does the function have an x-intercept? Okay, well, let's just think about this. An x-intercept means that you have a 0, right? It means you go through the x-axis. Well, if I have a -4 and a 5, I'm going to have to go through 0 in order to get there. Now let's look at this graphically if you didn't understand that. I have f of 2 equals -4. 2, 1, 2, 3, 4. There's my f of 2 equals -4. Now f of 3 equals 5. 3, 1, 2, 3, 4, 5. There's that dot. Does the function ever have to have an x-intercept? Well, for me to go from here to here, and the function is differentiable, all I really need it to be is continuous, yeah? I said differentiable, that means it's continuous. In order for me to go from here to here, I have to cross through this line. There's no other way. Now, I could cross through the line more than once because I could go up to it and I could start going up and down, but I have to go through this line at least once in order to go from here to here. And that's what the IVT is. So if they asked you something like this, you would say an x-intercept is guaranteed by IVT between, now you got to tell them what x-intercepts we're looking between. We're looking between 2 and 3, right? 2 and 3. Between 2 and 3, since the function, remember the function had to be continuous, okay? So that's what you would say. There is an x value guaranteed by IVT between 2 and 3 since the function is continuous. And so, like, same idea here. If f of x is differentiable, and f of -2 equals 4 and f of 3 equals 5, does the function have to have an x-intercept? Well, let's think about that on a graph. F of -2 is 4. And f of 3 is 5. Does it have to have an x-intercept? No. It doesn't. To go from this point to this point, I don't have to go down here. Now, could there be an x-intercept? Of course. Maybe the function goes like this, okay? But it doesn't have to go like that. It can just go like that, and then there's no x-intercepts guaranteed. So on this one, you would say, no, there is no x-intercept guaranteed, like following this exact same method here. No, there is no x-intercept guaranteed by the IVT, since the function -2 to 3, it never goes through the x-intercepts. Yeah, it never has to go through the x-intercept line. Okay, let's go here. Name all the theorems and define them. Okay, so we already did that pretty much. It's MVT, and that means instantaneous rate of change is equal to the average rate of change, and IVT, which means you have to cross through everything in between. Now remember, MVT, you need to be differentiable. IVT, you just need to be continuous. And this is the in-between theorem. And there is one more, I don't know if you remember it, EVT. They don't really ask about this one. It means that it has to be continuous and closed. And remember, that just means there will be a max and a min. They don't really ask questions about this theorem. They use it. They use it, but they don't ask you any questions about NVT really. So I wouldn't worry about this one too much. I would worry about these two. These are the ones that they most likely ask, okay? And the easiest way to remember these, MVT deals with slopes, okay? IVT deals with points. And if if they ever do ask something about EVT, it would be dealing with the max and mins, okay? Max and mins. But we deal with this one when we're talking about those candidates tables and things, okay? So let's go forward here. I got a way that they love to ask MVT here, and let's just walk through it. If f of x is differentiable, and f prime is greater than 0, and f double prime is less than 0, and the point f of 0 equals 1 and f of 2 equals 3, what are some possible values for f of 4? Okay, so first thing you're going to want to do is probably tell yourself, what does this mean? The derivative is greater than 0. That means that the original is increasing, because remember this means slope. The slope is greater than 0. I know that the original function should be increasing. And what does the second derivative tell us? It tells us concavity, right? Concavity. Now if it's less than 0, that means it's concave down. So it's going to look like this, right? So I know that the original function is increasing and concave down. Now if you look at this concave down portion, this portion is decreasing, this portion is increasing. So I'm focusing on this. I'm going to have a function that looks like this. Yeah, that's increasing and concave down. So I am going to look at the points they gave me, f of 0 equals 1 and f of 2 equals 3, and find some possible values for it that would make it look like this. So let's just kind of think about the graph here. F of 0 equals 1. Okay, so that means I got a point right there. F of 2 equals 3. Okay, I want it to do this, right? Okay, now let's just start. I'm going to start at the bottom here. F of 4 equals 8. That would put it 4, 5, 6, 7, 8. That would put it way up here. Obviously, that would not keep to the concave down portion. So that would not keep it concave down. That would have had to been concave up. So let's look at 6. It'd be that same problem. 6 would be up here. Now, how do you know where it would have to look at? What I would do is I would look at the slope that it gave you. Now, if you look at the slope, we're going to have 3 minus 1 over 2 minus 0. That would give us a slope of 2 over 2, which is 1, right? Anything that would make a value, a slope, more than 1 would mean it would make it concave up. We want a value that's going to make it concave down. So like look at this one, f of 4 equals 5. If it was 5, that would make it linear, because it would have kept the same slope of 1. It would have gone up 2 over 2, up 2 over 2, would have given you 5, right? Because f of 0 is 1. Up 2 would have put it at a y value of 3, over 2 would have put it at an x value of 2. Now if you did that again, you would then be at f of 4 equals 5, and that makes it linear, but we don't want linear. We want anything less than linear. That'll make it concave down. So this gives you a slope of less than 1, and so does this. So these are the two values that would make it concave down and increasing. These would make it concave up and increasing, concave up and increasing, and this one would make it increasing and linear. So the only values we have that could be true are these two. That's it.